Okay. Hi guys. In in your optics lecture, you may find that um, okay. First, you were introduced. Uh, say if there is an aperture, and there's a screen far away, uh, then first you were introduced that as the distance gets long, um, and this angle theta can be approximated by uh, this the angle between this point uh, between this line and the horizontal, right? So those are the same by like small angle approximations, um, and this term is just sine of that distance d, right? So this is d sorry, so not sine of d, but d sine theta, and um, and the difference between these two waves is just e I k d sine theta, and we let beta equals to k sine theta. Oh, sorry, where uh, k is 2 pi over the wavelength lambda. Then what we have is that wave difference is just e to the I beta sorry, beta d in this case. And in general, the amplitude we get in the screen will be a function of beta, and that's equal to this that equals to the slit function as a function of x, right? As a function of x, e times I beta x dx, and this resulting pattern in the screen, the resulting pattern on the screen would be the Fourier transform of ux of the slit function. So that's Fourier optics, right? That's what you learned in lecture. And at some point in the lecture, at least according to my experience, a lens will suddenly come out. So there will be suddenly a lens, right, placed after the aperture, and you will get is that now the screen is not far away. It's in the focal plane, right? It's in the focal plane. So here the distance is f. Right. And then you have like parallel rays doing that. Um, so one of the questions that could be asked is what does lens have to do with Fraunhofer diffraction, right? And this question, the answer to this question is by placing the lens, you now have an exact Fourier transform, or let's put it the other way. So by putting the lens after the aperture, and by putting the screen at the focal plane of the lens, now the Fourier transform describes exactly what will appear on the screen, not approximately. Right? Remember when you have that aperture and a screen far away, you did approximation, right? The angle here, right? This angle theta is the same as the angle theta here is it's just an approximation, right? Because you assume that these two lines are parallel, but these two lines are parallel, but they are not, right? They meet at the same point, but because this screen is so far away, these two lines are parallel, and because they are parallel, those two angles are both 90 degrees. So that's a kind of a weird triangle. This kind of triangle is very common in physics, in high school physics competitions. And it's like a isosceles right angle triangle. So this triangle is very common to construct such a triangle to solve problems in a very ingenious way, and that's but here it is a common construction to basically approximate that angle to equal to this angle. Now, how to do that? Well, you just draw a line here, right? And because uh, because this two angles are both 90 degrees, so you have like a 90 degree here, and this angle is equal to this angle, right? So since you have you just zoom in, because this angle is 90 degrees, this angle plus this angle is 90 degrees, this angle plus this angle is 90 degrees, so this angle is equal to that angle. So if that's theta, then that angle is also theta. So we have theta here, and because this line is parallel to this line, and this line is approximately parallel to this line, so these two angles are the same. So this angle is theta, right? Yeah. So that's very detailed. If you find those details very very boring, then yeah, it's not necessary to bear with it. You can just close the window. Okay, and so the point is, here we're doing an approximation because the distance is very far, but here we don't. So here the approximation comes into the the e to the I beta x term, because theta is in beta, right? And that beta is the theta is being approximated, so beta is being approximated. So the whole Fourier transform is being approximated. It only works if there's no length. It only works when the distance is really far away. But now, if we have a length, then we can get exactly we can get the Fourier transform exactly right. So the Fourier transform exactly describes what happens in the screen, as long as the screen is placed in the focal plane of the lens. So I'll demonstrate why that is the case. Now, so yeah, say if you have like three slits, and here is the screen. You have a length. Now, so now you do a line that perpendicular to sorry, by convention all the extra lines should be joined in dash. Yeah, so this is perpendicular to all these parallel lines, and if you do this, you will find okay all okay, I'll claim that the optical path from this dashed line to this point is exactly the same for all these three light rays. Right? Why this is the case? Because remember your format principle. When you have a lens, the reason that right, so that's U, that's V, object, image. The reason multiple light rays can go from object to image is because of format principle. Format principle only allows the smallest optical path, minimum optical path from one point to the other. But when all the optical paths are the same, they're all the smallest. So there are like all these paths. So all these paths exist, right? But in this case, it's the same. If you imagine a point in infinity, and it emits like light rays that are essentially parallel, then from that point to that point, there will be like infinitely many light paths that are all the smallest. They all have the smallest optical path. So these three light rays must so from this point, this path, this path, and this path all have the same optical path. Now, if you look at left hand side of this dashed line, you will see that from this point to that point, from this point to that point, from this point to that point, all these three lines will also have the same optical path because of geometry, right? They must be similar. So not similar. They must be the same, and there's no like there's all like vacuum or air. Like there's no something with index refraction here on the left hand side of this this dashed line, right? So because the total optical paths are the same for the three lines, and on the left hand side of this dashed line, the optical path is the same for these three dashed lines. So on the right hand side, they will be the same as well, right? It's like yeah, it's just one minus the other. What's left must be the same, right? And so they have the exact same optical path, not approximated but exact. Now, the only difference between this aperture to this focal plane now arises from this extra path, not approximated but exactly. Now, when you have the path difference exactly equal to this theta times sine of this distance, then now this beta is no longer approximated, it's exact, and you will find that the Fourier transform is also exact. Right? So remember, originally when we have the long distance no length, right? We cut this like this, and we say okay, this is the path difference. But in fact, these two paths are not exactly the same. They are approximated the same. But in this case, if we cut it in this way, what's on the right is exactly the same. They have the exact same optical path.